This is a question predominantly about the alkanes topic. It also touches on haloalkanes. I'm going to recommend you work your way through the question, try each section before you continue the video to review the answers. So here's parts A and B. Part C. Part D. And we're then ready to start reviewing the answers. So, first one, an equation for the combustion of heptane in an excess of oxygen. We're told what heptane is. We know that in combustion we're reacting with O2, and we know that it's excess oxygen, so it's complete combustion, so it's CO2 and H2O. I would then always follow the rule of Cho when you're balancing hydrocarbon combustions. You balance the carbons, then the hydrogens, then the oxygens. So I need 7 CO2. I've got 16 H's, so I will make 8 H2O. And that leaves me with 22 oxygens on the right hand side, which means I need 11 O2. Part B is predominantly factual recall. You simply have to remember this. The catalyst for catalytic cracking is zeolite. And the conditions other than the high temperature, which you're already told, is that there is a slight pressure. The final question here is fairly common. We are told we're making heptane, which we've already been given. We're also told we're making cyclohexane, which you would need to know is a functional group isomer of an alkene, so it would be same general formula as an alkene, C6H12 from CnH2n. So we have that, and it's then simply working out what's left. And I've got 3 carbons and 6 hydrogens, so I'm also making propene. On to part C. Alkanes can be used in free radical substitution to produce haloalkanes. Give equations for the propagation steps in the reaction of butane to form 2-chlorobutane. Now, what you've got to be mindful of here is the fact that we are asked specifically about 2-chlorobutane. So we are going to need to use structural rather than molecular formula. So if I draw out my butane, my chlorine radical is going to rip an H away on the second carbon, which is where the chlorine can then be added on. Moving on to part D, and we've got chlorofluorocarbons, CFCs, and we've got the structure of a CFC here. We've got a trichloro, trifluoro, ethane. Now, with the aid of equations, why can a single radical cause the decomposition of many molecules of oxygen? Now, once again, we are dealing with a chlorine free radical. The equations are direct from textbook, direct from notes, and you do have to know these equations pretty confidently. Now, what you can therefore see, if I break it down in one way, I can combine those to see that I've got 2O3 going to 3O2. Now, that in itself shows us that the chlorine and the ClO radicals are regenerated. They're not a part of the final overall equation. But you can also see it from here that the Cl radical is regenerated.